I'm Madeline Stalder. Today I'm going to be going over some nanophononic metamaterial implementation to improve thermoelectric device efficiency. I have a student collaborator on this project, Koby Vargas, and we're working under the advisement of Dr. Jessing from Fort Lewis and also under Dr. Hernandez-Charpak from CU Boulder. And this project is funded by NSF PREM, known as PEAQS. Okay, so first, some motivation and intro to the project. Our overall goal is to increase the overall efficiency of thermoelectric devices. First of all, because this provides additional energy generation across the grid, and these devices are currently a really big key area of interest in the energy generation field. And one of the main reasons for that is because they're applicable anywhere that heat is available. So that's in waste heat recovery from power plants, that's automobile exhaust and emissions. There are cool applications for harvesting heat given off by the human body and using that to power your phone or something. There's also really extreme environment applications such as extraterrestrial rovers, as well as Antarctic power generation. So these thermoelectric devices are solid-state devices that convert a temperature differential into electrical potential through a process called the Seebeck effect, or vice versa, which is the process called the Peltier effect. In this study, we focused on thermoelectric generators.
The people who, so they funded our.
Okay. I thought that was a question. Okay, so in this study, we focus on thermoelectric generators, or TEGs, which convert heat to electricity. These devices are a thermoelectric material sandwich with N and P-type materials, where N-type corresponds to a material that has been altered so that it has more electrons than holes, and P-type is a material that has more holes than electrons. And here, these holes are positively charged entities with a charge equal in magnitude but opposite to that of our electrons. So if we look at, I think you can see my mouse, this schematic here, we have our hot region and our cold region, and here's our N and P type materials with predominantly electrons here and holes here. And as a result of this temperature differential, our charge carriers diffuse towards this metal, this is an electrode that connects our plates. And we get this charge buildup down here that induces an electrostatic potential, which causes an external circuit to have current running through it, which we can harvest. So thermoelectric device efficiency is characterized by the figure of merit, or ZT, which is given here. And it is based off of our Seebeck coefficient, electrical conductivity, absolute temperature, and our thermal conductivity. And this figure of merit is really cool because it's a way for us to directly compare efficiencies of a wide range of energy generation technologies. So if we look at here, this is hard for me to see with all these cameras. We have comparisons of a lot of modern energy generation technologies. And if we look at modern thermoelectric devices, they have ZT values of about 1 to 2.5. So if we compare that to this coal cycle here, which has a ZT value of a little bit less than 20, we see a really wide gap there. And that's generally due mostly to poorly performing thermoelectric materials. So the question comes into play of how we can improve these efficiencies. If we look at our thermal conductivity here in our figure of merit, we see an inversely proportional relationship. And then on top of that, if we compare the orders of magnitude of each of these parameters, we see that thermal conductivity actually has a much larger impact on ZT anyways. So we hypothesized with this information that if we can reduce our thermal conductivity without negatively impacting our other material parameters, we can observe an increase in ZT. The question then comes into play of how we can specifically target only the thermal conductivity. So studies show that through nanostructuring the active area of a TEG, the reduction of thermal conductivity ensues. One study actually estimated an increase in ZT of up to 193% through intensive modeling due to the introduction of these nanostructures on the thermoelectric substrate. In a separate study, we compare uniform silicon, in this case, to nanostructured silicon, shown here in the red, and it shows a direct correlation, further a drop in thermal conductivity with those nanostructures being implemented. So what is nanostructuring? This is the confining of critical dimensions of a material or a device to, in this instance, less than 50 nanometers. This is done through a process called electron beam lithography, or EBL, and this is the scanning of a focus beam of electrons, which is inside a scanning electron microscope, to essentially draw custom patterns on a substrate that are coated with a resist layer, which is an electron beam sensitive polymer usually. So this is an image of the scanning electron microscope that is in the nanofabrication laboratory at FLC that we've been using to draw these patterns with EBL. And just for a size reference, this is a human hair, and there are 100,000 nanometers in the diameter of the average human hair. And so we're aiming to get sub 50 nanometers in our dimensions, just to kind of put that into a little bit of reference. So how does nanostructuring actually affect our thermal conductivity? Well, if we step back and look at how heat propagates in a material, in a semiconductor specifically, we see that the primary thermal energy carriers are phonons, which are these vibrational packets of energy that propagate at the nanoscale. Now, these phonons oscillate with multiple frequencies and traverse the material in multiple directions. So if we look at our schematic here we have some phonon electron scattering that's going on, and over here we have phonon scattering, and they're going every which way, and it ends up being extremely chaotic within a material. And because of this, it makes it extremely difficult to predict and control these phonon behaviors. However, it is by fabricating a material in a way that specifically allows the targeting of the majority of these phonons that it becomes feasible to restrict their movement. And it is through specifically engineering this material in a way that we actually achieve the status of a nanophononic metamaterial. So these nanopillars interfere with phonon dispersion in a thermoelectric substrate such as silicon and effectively lower their group velocities, density of states, among a ton of other properties at each pillar's location. This means that if the phononic movement is reduced, we end up with lowered thermal conductivity, so it gets a check mark. Further, the flow path of our electrons is uninhibited. If we look at this schematic that I cannot see with the images in front of me, we see our nanopillars on top of our thermoelectric substrate, which is where our electron and hole propagation actually takes place. So these nanopillars don't affect our electron flow at all, which doesn't affect, in theory, our electrical conductivity. So that also gets a check mark, and we note here that we've checked off both of the stipulations we put forth in our hypothesis. So if we focus solely on the group velocities of these phonons for a second, just to kind of further show how our thermal conductivity is being reduced, we have our thermal conductivity over here, followed by our group velocity in here. So we see that relationship almost immediately. And there's this other stuff in here, like our phonon-specific heat per unit volume. This is a reduction function that takes into account all of the phonon scattering that's taking place. So if we look at our group velocity here, if it goes down, so does our thermal conductivity, which is exactly what we had wanted in the first place. So then we moved on to being able to test these materials and monitor them throughout the nanofabrication process. The problem, though, is that FLC doesn't currently have the means to monitor something like thermal conductivity in these devices. Further, due to the nature of thermoelectric devices, electrical conductivity of them cannot be measured with your conventional DC meters. This is because the device will begin heating up once a current is applied to it. You know, that's its job. It just starts acting in the reverse direction, and that's where we see that Peltier effect kind of come into play. So because of this, an alternating current resistivity meter or similar instrument is required to actually measure this parameter. So the solution was we build our own. So information gathered from a commercial TEG manufacturer enabled us to build a testing instrument capable of measuring thermal conductivity. With that information, we built this very rough schematic of what we needed to build, utilizing this equation over here, which took into account a known ratio of input power into the TEG, the thickness, and then knowing the temperature at each of these two interfaces. Knowing this information, it was relatively simple to back calculate and get our thermal conductivity out of it. So this is the testing instrument that we ended up fabricating, powered by an Arduino Uno microcontroller shown here and here. And that previous schematic is actually inside this whole circle, where here's our TEG and underneath is our heat source. And in here is melting ice, and it's being compressed so that we can get that compression to encourage our thermal flow throughout the entire system. And we use melting ice, because if it's melting, it's at a constant temperature, and that enables us to really easily know what the temperature of that interface is. And we can still jam enough ice in there that we can get enough compression to really encourage that flow. So here's a semi-futuristic iterative fabrication sequence that will take place for each of our devices. To simplify it down, we have a glass substrate with thermoelectric material 1 and 2 on top. It goes through a round of electron beam lithography and a second round of thin film deposition to get rid of these guys in here. And then after a second round of EBL and what's known as thermal evaporation, we get our metal on top. And after getting rid of that, we end up with a schematic that looks almost identical to the first one that we showed for a thermoelectric device. Now, for the time that I spent here, I was able to take a silicon substrate and through a process called spin coating, I could layer, it was about 200 nanometers thick of PMMA on top. And PMMA is that electron beam sensitive resist that I first mentioned. And I got to see it go through EBL where it was exposed to an electron beam. And after development, I got this positive nano pattern formed on top of the PMMA. And in the future, we'll be able to go through thermal evaporation, which we do have the capability for it at FLC due to technical difficulties with the evaporator. And then of course, COVID, that was not able to happen, although we were very close. And then following it goes through liftoff, where you're left behind with your nanopillars or your nanostructures on top of your substrate. So here are some electron beam lithography results. Here, these are some nanoscale dots with diameters less than 35 nanometers. And these dots actually form the foundation for our nanopillars that after evaporation and liftoff will be formed on top of our substrate. We also got some nanoscale lines. Here we have the FLC Skyhawk logo, about 11 microns in width. And remember that your hair is generally about 100 microns in diameter, so very small Skyhawk. And then if we zoom in on his eyeball, we have some nanoscale lines that are 37 and 78 nanometers in width. That is also very promising dimensions. Future directions for this project include the continued optimization of EBL to afford smaller dimensionality in our nanostructures, as well as the completion of our testing instrument in order to accurately monitor thermal conductivity of our devices pre and post nanostructuring. This instrument may have the capability to also give feedback on current and voltage stats so that we can backtrack our electrical conductivity there also and make sure that it's not being negatively impacted by our structures. Future directions also include progress with establishment of methods to build nanopillars. That includes getting our thermal evaporator up and running and then establishing a method for liftoff to leave behind nothing but those structures on top of our substrates. A last really important future direction is the incorporation of a PN junction into our substrates to more accurately mimic a true thermoelectric device. Studies so far have taken place only on P-type silicon, but ideally we really want that to be an N and P-type substrate so that we can really mimic how a true thermoelectric device works and our measurements will be a lot more accurate. So to conclude, nanophononic metamaterial, or those nanostructure implementations, it's a viable route to increasing thermoelectric device efficiency. We see phonon propagation restriction that results in reduced thermal conductivity. Further, testing instrumentation for monitoring of various thermoelectric device properties has been established and can be built on, as well as successful fewer than 60 nanometer structures achieved with electron beam lithography. Future directions include more advanced testing and further implementation of nanopillars. I want to take a small second to thank my advisors, Dr. Jessing and Dr. Hernandez-Charpak, who I don't think is viewing today, for all the help with them, and also Koby, you're out there, so shout out, thanks for all the help. And again, this was funded through NSF PREM grant called PEAQS. References and questions.
Hi, Maddie. This is Dr. Williams. So you did get your testing device built, is that right? But you couldn't get your structure made?
Correct. Yes, the testing instrument has been built. Preliminary tests show we need a little bit better source to actually be able to get it working. But no, the nanostructures themselves, due to the technical difficulties with the evaporator and then COVID happening, the EBL is as far as we were able to get.
Yeah, I was just wondering, with the device that you did make, were you able to test, you know, an existing TEG, one that hadn't been nanofied, or however you want to put it.
Nanostructured. Yeah, so we, from that same company that kind of pointed us in the right direction on how to test these, we actually bought from them 2 commercial thermoelectric generators for preliminary testing purposes, just to make sure, you know, our instrumentation is working. We were cut short right as preliminary testing on that was taking place, and as it became evident that, you know, primarily a reliable voltage source for the instrument was definitely needed and could not be obtained on home appliances.
Got it. Cool. Thanks.
Yeah.
Hey, Maddie, this is Dr. Lee.
Hi.
Hi, I got a quick question for you. So for the material for the nano pillars, why did you pick up PMMA? Are there any other alternatives are better than that, or what's the reason you pick up that material?
So PMMA specifically is very popular with electron beam lithography specifically due to the resolution that you can get with your patterns with EBL, and also because it's just a really widely used resist layer scheme. It's just really popular with EBL in general, due mainly to the resolution that you can get.
Okay, but that's a photoresist, right? But what are there anybody using, for example, metal pillars or any other material?
Right, so the PMMA will actually be developed away and actually won't be a part of the device at all. We will fill in, and the pillars themselves will be like aluminum, I think is what we're going to progress with.
Got it.
Yeah.
Right, makes sense.
And this is Nico here. I don't know if you can hear me.
Oh, you are here. Hi, Nico.
Of course, yeah. Just to kind of provide more details on that answer. So one potential question, PMMA would allow us to go to very small scales. And there is a potential theory that just the sheer size of things, that you get a coupling from the phonons of the resonance of the pillars. And so even PMMA could have an effect on transport in the film underneath. And then if that won't work, then we were going to go to like more dense materials like metals. So that's Maddie was saying. Yeah, Maddie, great job.
Thank you.
Thank you. Got it.
I have a question. This is Jerry Crawford.
Okay.
So the nano pillars, is the spacing crucial to being able to cut the thermal conductivity down in particular ways? Are you getting some sort of resonant phenomena down in the layer below because of that?
Good question. I think that might be something that we'll have to kind of play with as we build our nano dot arrays on top of these substrates. If I had to venture a guess, I would say, yeah, absolutely. You know, you're going to get those local resonances, and as they're bunched all together, you're probably going to get a different effect. I can't say if it'll be a better or a worse one, but that'll be about something that we have to play with in future studies.
And then a second kind of follow-up to that. The thermal conductivity you measured first was, or they were talking about first, was for the P&N materials. And if you put the nanopillars on top, then as long as they don't conduct well, then you'll have a lower thermal conductivity. How do you decide what that means in terms of lower thermal conductivity? Are you measuring still in the N and P material, or are you measuring through the pillars?
So the way that our testing instrument was set up is that we have the heat flow through the entire system. So before and after measurements will be taken through the whole TEG as a whole. So that takes into account the PN junction and the nanopillars on top. So we're kind of playing with how it flows throughout the entire thing. Does that answer your question?
Yeah, obviously I'm not quite clear on how to even ask the question. It just seems to me like if you don't change the thermal conductivity of the N and P materials directly,
right,
then I'm not sure it enhances the process. But I think what's going on with the nanopillars may have something to do with actually changing the thermal conductivity of the N and P material. It'd be interesting to try to measure that without the pillar interfering with what's going on with the measurement. You know what I'm saying?
I think so. Nico, you look like you wanted to add.
Oh, I just wanted to say it could be that it's just because you measure like heat cold like through the film, and then you go kind of left to right, or sideways. and then you have the film plus nanopillars on top. So hopefully, and then if there is a difference in thermal conductivity due to the presence of pillars, that would be great. But that's what we hope to achieve, I guess. But then doing that without affecting the electronic conductivity, I guess there is that dual thing, because as you said, it's not obvious what the effect of the pillars will be as function of spacing and size and heights, because of materials and defects and the quality of the surface. But yeah, I guess that's what they were building the setup to be able to do. I don't know if that makes any sense.